What's up, everybody? Now we are going to focus on SSV computation and says also for a fixed frequency, right? Usually, I'm going to iterate what I just said in the previous video where we computed SSV for a given specific complex n by n matrix, right? And we did that by using fmincon, and fmincon is a Matlab function where we use when we try to optimize stuff, right? And in addition to that, when the problem that we are dealing with is, it has some certain properties. What kind of properties? Well, continuity and fmin for example, con is for constraint, right? And min, it tries to minimize stuff, right? It's an objective, and you usually use fmin when you can express the problem in a closed form, right? And that's very vague definition. I'm aware of that. However, let's say if you think that your problem, your objective, let's say this is J and your variable is X, right? Optimizer, decision variable, right? And this is your cost, for example. And if you think that you can analytically compute the derivative of your cost function with respect to your decision variable, and in addition to that, you also can compute like the Hessian, right? And you have the case where these are like something like that, analytic, right? Or polynomial rational or something, right? Okay. The problems where you don't have a lot of discontinuity, and again, I'm aware of that. That's very vague definition. And let's say if you have some formulas, right? And just try to use fmincon, right? It's quick to formulate, quick to code, right? And just try to use that. And if that doesn't work, if you get like extreme and exciting errors, right? Try to use GA, genetic algorithm, right? Just try that and see what happens, right? And enough with optimization, right? In the previous video, we just computed SSV, structured single value, for a given n by n complex n matrix. Okay, and we did that with fmincon just to kind of understand the problem better, right? And for example, that was our situation, right? Let's say n, let's call it n, and minimize d. We define some d set for a given data set, right? And then something like this. That was the problem. And we parameterize our d variable, decision variable, right? And by using the structure of the d set, and by using fmincon, we computed SSV for a given n. Okay, now we are going to use Yalmip. Yalmip is an LMI solver, right? And in addition to that, and whenever you have a LMI problem, you also need some type of STP solver, right? And my STP solver is called STP T3. There are other solvers for example, Mosaic, right? And that's it. That's my, and I also use Matlab 2020, Matlab 2021b. Okay. And all right, now we are going to try to focus on this problem, and especially the upper bound aspect of it, right? And we are going to formulate that problem in LMI form. Okay. And because what Yalmip is capable of is dealing with LMI problems, right? Constraints that are in LMI. What LMI stands for is linear matrix inequalities. Okay, so it has to be linear. For example, D and D inverse, right? And minimize D in given D set. This is in and of itself, it is not in LMI form. It is not linear, right? And that, let's just focus on this term, for example, D and D inverse. It is not linear, okay? So, because our D is our decision variable, right? Okay, and it is actually more complicated than a typical quadratic form. Let's say D transpose and D or something. That will be the quadratic form, and that even wouldn't be counted as linear. And of course there are ways to turn this into a linear form. However, this is complicated. This is not linear, right? Is what I'm saying. Okay, so let's get rid of this, right? Okay, and in the previous video we did it, and we also checked the Matlab codes to do that. Okay, and now we are going to do the exact same things, right? Just by using Yalmip. Okay, so for example, that's the first thing that we saw in the previous video, right? Again, we have a 2 by 2 transfer function matrix, and for a given frequency, 1 radian per second, for example, we have that, right? And this is, again, let's just call it, for the sake of argument, this matrix N, and N is 2 by 2 complex matrix. Okay, and here this is TF, transfer function matrix definition in Matlab, right? And this is for a given frequency, and just give me the complex matrix that corresponds to the frequency that I'm entering, right? Okay, so ever frequency, and this is the output. Again, this is 2 by 2 complex matrix. Okay, of course, for the sake of examples, demonstration, right? For the sake of demonstration, this is fairly a small scale problem, right? And for there is some example that is not so small scale. It's like 7 by 7, right? Its dimension, and that I think is close to a real life example, and as complicated as necessary, right? And now we are going to look at a couple of examples one by one. The examples that we saw in the previous video, we use FMICON, and now we are going to Yalmip. We are going to solve and focus on the exact same examples, right? Okay, and that's why I wanted to make that. That's why I really, that's, I think, is important. You kind of need to be able to solve a same problem in, at least two ways, right? There are a couple of reasons for that, why you would like to be able to solve a problem, the same problem, in two different ways, two different computer programs, for example, or two different algorithms, for example, right? Because sometimes you might be making some mistakes, right? Let's say you use a algorithm and a computer program, a program, right? And you get some result, let's say 3, okay? And after that, you solve the same problem by using B program, right? B program can be an algorithm, it can be some, let's say A can be fmincon and B can be Yalmip or something, right? That kind of stuff I'm talking about. And if you get like 2, you would immediately see, hey, there is something wrong, right? And then you would check your A computation and then B computation, and maybe the result is 5 or something, right? Maybe you are making some assumptions, and since you use different program or solution method, right, you kind of notice that. So that type of redundancy is helpful, and again, that type of redundancy can help you realize, hey, you are making a mistake somewhere, right? And okay, that's a little advice. And now let us focus on the next issue, right? Okay, this is our case 1. Okay, so we have n, again, complex 2 by 2, right? And we want to find this, right? Compute SSV, structural singular value, right? And here, this, the uncertainty is in this form, right? And it is not bounded at all, right? For example, sometimes you see that type of version, that type of uncertainty, just delta, right? And delta again, complex 2 by 2, and in addition to that, it's like bounded, right? So it's like B stands for ball, right? And sometimes you have like the exact same thing, right? But you have like O, as in open, right? Here again, delta is in complex 2 by 2, and like norm is less than 1, okay? So the reason why I'm focusing this, you can see these type of kind of notations, right, in publications and some books, right? For example, in Zhu's book, right, Kemin Zhu and John C. Dial, Essential of Robust Control, is like a kind of the standard textbook in like robust control, right? And if we're talking about non-LMI type of books. And okay, so this is case 1, and we are focusing on full delta. When we say full, we mean unstructured uncertainty, right? It's like this type of uncertainty we are talking about. Again, for a given delta set, uncertainty set, we have a D set, corresponding D set, right? And we talk about the rules, right? And that's why I'm not going to detail them anymore, okay? And for a given full delta, our D set can be parameterized as such, right? D times identity. We have only one parameter to think about. And if you think about it, although our uncertainty is not constrained as the other cases, right? Now we're going to see a couple of them. The solution to get SSV is, I mean, this is the best solution. I mean, this is the best problem to solve manually, right? In a way, in a sense. Why? because we have only one parameter, right? I mean, you can just, if you don't know anything about optimization or control or SSV, right? If you don't know anything about this, you can just directly plot D, right? For a given D, right? Compute, what do we need to compute? Yeah, compute this, right? Because D can be parameterized by a just single parameter, D, small d, right? Okay, here, yeah, here we can see that. Give me a D and I'm going to give you the cost, and this is the cost, right? Let's call it cost. Okay, and by using such arguments, right, you can just compute SSV. So in a way, full delta case, uncertainty case, is the simplest, right, case where you would solve. Okay, because again, you have only one parameter to think about, only one knob to tune, right? Okay, so now we are going to focus on the Yalmip syntaxes, etc., right? And by the way, before that, and I should also say that, let me just show you one sec. Here we can see this is Matlab mu SSV output, and this is Yalmip output. And there is also, again, spectral radius, right? And sigma max. And you can realize that 0.9152, right? And this is again 0.9152. And by the way, first of all, this to agree, right? And that's a good thing, right? Again, you need to check that to revise, to control if you are making some mistakes in some algorithm, right? And that may be the case where you are making mistakes in both algorithms. So, okay, and we also realize that sigma max equals to SSV, and that's a special case actually, right? So when you have full delta, your SSV, let me write it, your SSV is, you can just directly write that sigma max of n, sigma max of given complex n. Okay, and again we have one more special case like that, and but before that, let's just focus on the Yalmip. Okay, this is Yalmip code, right? Yeah, this part is the Yalmip code. Okay, so first of all, we are just defining our n matrix, and we are computing to get our n, this n matrix, right? Just a constant n matrix, complex. And after that, it is better for us to just okay, this is the first problem, right? So just give me 1 second. Okay, I'm going to show you before explaining this code. I'm going to show you another thing. Yeah, it's here. Okay, just try to focus here. Not even here. Okay, this is the, all right, let me get it close to that location. Okay, this is our problem, right? Okay, and let's say gamma is bigger than this cost function. Okay, so we are just expressing our optimization problem in a kind of geometric way, just to be able to do bisection, right, type of algorithms. And this is the kind of arguments you see in optimization, right? And here we use this identity, right? Sigma max of a given matrix is like the 2 norm. All right, so let's square both sides. Okay, here nothing new, right? And again, this equals to that. Okay, maybe. Okay, the terms are clearly close. However, this is equals to that, right? Okay. And by the way, this is also equals to that. So I'm just writing the same stuff over and over again, okay, just to make things clear, I guess, but it's not that clear. All right, and then we get this equality, okay, and from that I would just write directly, right, just from the third expression, maybe. I wanted to make that type of redundant statement, right, just to make myself, I guess, smart. All right, and here just distribute that transpose term, right? Okay, so nothing changed. And now just group the d transpose d term, right? Again, we haven't changed anything, right? Okay, and then just try to focus on this d inverse term and post multiply both sides of the equation by d, right? Here d, and again do the same thing to that d inverse transpose, right? Again pre-multiply both sides of the equation by d transpose here, and after that you have this term. Let me just clear some scribbles, okay, and so just d is our decision variable, right? And here we can see d transpose d and d transpose d, d transpose d, right? And we can just use that type of variable change, and our problem would turn into a LMI. For a given, gamma is SSV in a way. However, this is a bisection. In and of itself, for example, let me just make something clear. If you say that gamma is my decision variable and also x is my decision variable, this is not an LMI problem, right? Because this term is not linear. You have some decision variable and decision variable multiplying each other, right? And this is no bueno, right? And not linear. So, however, gamma is something. Gamma is scalar, right? Here, that's gamma. This is gamma, right? And by the way, we also know that gamma can't be less than 0. So let's start at from 1000 or something, right? And just here, just put 1000 and try to get x, right? Okay, maybe just let me do that. Okay, now this is our problem, right? And just give me one gamma and I'm going to show you if it is feasible. Okay, and then a really small gamma, just try like 1e minus 3, for example. Is it feasible? Yeah, feasible. And then just try this location, right? Feasible, again feasible. Okay, so try this, dot dot dot, and then you will reach to your correct data. That, sorry, what? Gamma, right? Gamma, okay. And for a given gamma, find an x. This is the feasibility problem, and this is a bisection and feasibility problem. Okay, this is our problem, right? This is a typical bisection problem. Again, r is a positive number, and x is not like something like this. X has some structure, and like d had some structure, right? And d had some structure, and x is d transpose d. So X has a structure that is related to this structure, and now we are going to talk about that, right? Let me just delete them. So first we need to determine the structure of uncertainty, and I'm going to be like really redundant right now, and then determine the structure of D, and then determine the structure of, let me write something like this, X. Okay, all right. So this is like the basic algorithm that we need to implement. Okay, so this is our original problem. Here we know, first of all, we know we have gamma square terms, right? Okay, what was the problem? The feasibility problem. M transpose X, M, or M n, right? Okay, don't. Let us not worry about that. This is our problem. So I call it G2. Okay, I call it G2. And again, epsilon, we know what epsilon is. We use that type of, since we can impose like strict inequality, right? We usually, what we will do is, and I'm not going to write gamma square either, right? I'm going to write G2 identity less than or equal to, again, minus epsilon 1 times identity. Okay, so we will do something like that because we can't do less than 0. Okay, due to some numerical issues, right? And here D1, and we know what D1 is. Okay, D1 is this. Okay, since we have like full unstructured uncertainty, okay, our D set is D, just a D is D times identity, and D is like a positive real number. That's it. Okay, so that's the all. And symmetric also is like real. So if you just want to, this in and of itself is, it means in real, but we also need to state that it is a positive real number, and in a moment we are going to impose that constraint as well. Okay, all right. So here, and just look at this, and then I'm going to show you something. Just what was X? X is D transpose D, right? Okay, and what's the structure of D? D times identity, right? Transpose and D times identity. Okay, so D transpose D times identity, right? Okay, so again, let's call it D hat or something. Okay, and again, what is the structure of D hat? It is again a positive real number, right? So we just call it D1. Okay, we just call it D1. So D1 times identity, again, X is D1, and where D1 is in positive real numbers, right, times identity. Okay, and 2 is the dimension of the problem. Okay, let me delete all of them. I'm deleting like some statements, and then I'm writing the same exact statements, and I feel like, I mean, that's both redundancy and also necessary if you are trying to learn, right? And all right, some people learn quicker and some people learn like slower. So okay, so F is our constraints, right? And just try to look at this expression. Just try to look at the expression and recall and transpose x and minus g2 identity. And since we cannot say less than 0, right? And we would like to say less than or equal to minus epsilon 1 identity. Okay? Because we want to impose the negativity constraints. Okay? And this is exactly the same thing, right? If you check that, this is exactly the same thing. Okay? But we also have that constraint where d1 is in real, and we impose that by using that line. But we also need to impose that d1 being positive. Okay? And here d1 being positive is given here. And by the way, this is like not correct. This is not Hermitian. It is, but positive. It is positive. It's not a matrix either, right? Okay. So I am looking at this, and you would usually write this, right? Just STP settings and your STP solver, the name of your STP solver. And however, since we are solving bisection, this is like a kind of special type of optimization problem, right? There are bisection modules, I guess the correct way of saying that. And if you are using Yalmip and also your STP solver is STP-T3, you just write that. And if you're using other type of STP solver, right, and just check the correct syntax, right? Because in that syntax, in that line, you're basically saying, hey, I am using STP-T3 as my STP solver, and this is the problem that I'm entering is an bisection problem. So this line kind of means that. Okay, so let's not worry about the specifics. And here, bisection, and we are not saying optimize, right? We are saying bisection, right? F is our constraints, right? And G2 is the term that we optimize. Okay, and remember, we're trying to minimize G2. G2 is gamma square, by the way, right? Okay, and here are the options. Okay, so and then we can look at the sol.info to see if there was some mismatch or something, right? Any problems. Okay, after we get the solution, we look at the x, right? This x, and then G2, and then don't forget to get the square root of G2, because we have gamma square and we like to have gamma, right? And I call it Yalmip SSV because this is the SSV value that Yalmip gave us, right? Okay, again, as in the previous cases, right, we also computed spectral radius and also sigma max. This is like this type of here. Okay, and again, we are writing them, printing them, right? Okay, this part, this is like Matlab mu SSV function. Okay, and 2 by 2 because it's like our uncertainty has that structure 2 by 2, right? There is no structure at all, 2 by 2 complex. Okay, so you are entering your structure of the uncertainty. Okay, and Matlab mu SSV gives us mu info, some information, right? And also bounds, right? and you have lower bound and an upper bound, and we are trying to, in that module, right, in that video, we are focusing on upper bound, right, and that's why we get the second of it, second bound, and that's upper bound. Okay, and then print them, right? Just now the solution here, 0.9152 and 0.9152, right? And again, sigma max, these three are equal, right? And that was the first problem, and now we are going to focus on the second problem. And okay, this is the repeating scalar diagonal delta. This is the easy, I mean, I would say easiest structure, again, but one of the easiest to compute, right? Because in that case, let's just, before saying anything, right, here, look at this, 8680, right, and 0.8680, and first of all they are equal, and that's a good thing, right? And after that we realize that that's equal to 0.8680, and that's actually the special case, right, for that type of uncertainty, right, for that type of uncertainty, the SSV value is actually the spectral radius of n. Okay, here this is our delta, right? This is repeating scalar diagonal delta case, and here this is the structure of our D set, and here this is the corresponding D set. For a given repeating scalar delta, our D set has this form where it comprises of D positive definite Hermitian matrices, right? Okay, this is complex, positive definite and Hermitian. Okay, and these are the things that we know, right? And again, I'm looking at this, I mean, this was the case we use in in the previous video, right? In the previous video we were using fmincon, right, to compute SSV, and for that, to make things easier, we parameterize, right, our D matrices, right? And but we don't necessarily, we don't need to do that type of specific, this is like a little specific parameterization, right? We are just expressing our decision variables in positive real numbers, right? And we don't need to do that type of specific parameterization, right, if we are using Yalmip. Again, this is the, if you look at this, this is the right argument, and we are going to look at this in the last case, right? And okay, again, we are aware of that, and what we have is a bisection and feasibility problem. Okay, so since D is a Hermitian, first of all, since D, like this D, when I'm saying D is Hermitian and positive definite, and X is D transpose D, right? And or D Hermitian D, right? And what we have, X again is positive, X is complex, and also X is an Hermitian matrix, right? So So here x equals to this bolt D and this bolt D. It must be complex n by n. Okay. There is a typo here over there. Okay. So let's continue. Let's look at the code, right? Here again our transfer function and our n complex matrix. Again we define our bisection gamma square, right? Gamma square, and again epsilon for numerical accuracy, right? Or numerical requirements, and x is DHD, right? And D is positive Hermitian and D is positive Hermitian, right? And then we will call it D1, and that D1 is Hermitian and positive definite. Okay, so that D1 is that, and the dimension of the problem is 2 by 2, and this is Hermitian and complex. Okay, so we are talking about this D1. Okay, here x equals D1, and here just f is an object where we put our constraints, right? And let's look at the constraints. N transpose x n minus g2. Again g2 is like gamma square, right? Identity, sorry, not identity, like x, again x, and right, negative definite, right? Okay, here this is that corresponds to that line. Okay, and again we also have that positive, like D1 being positive, right? And that's being imposed in that line. Yeah, that's correct. D1 is Hermitian, complex, and positive definite matrix. Okay, and again the same line to state that we are using SDPT3, and this is a bisection type of optimization problem, and that's why the Yalmip syntax, like bisection, and we put our constraints and then we put our bisection variable, right? And then object options, right? And STP settings, and then we finally check solution.info just to see if any error occurred during the iteration, right? And after the solution we get our x and g2, and g2 is like gamma square, right? And then we get the square root of it and we call it Yalmip SSV. Okay, and as in the previous case we check spectral radius and sigma, right? Sigma max, and here this is Matlab's mu SSV function. And what was our, let's recall that, what was our uncertainty? Our uncertainty was the easy case, right? Delta times identity, where delta is in complex, and this is identity, right? And usually you would type 2 by 2, but since this is a repeating diagonal case, you would make the second argument 0. Okay, so that way Matlab's know it is a 2 by 2, 2 by 2, however repeating scalar case, repeating, sorry, not scalar, repeating diagonal case, right? When you type 2 comma 0, Matlab knows that this is like delta times identity and 2 by 2. Okay, Matlab gets that idea. Okay, and again we focus on the upper bound and we print them on the screen, right? And we can see that they are same, and that equals to the spectral radius. Okay, now let us focus on the third problem. And okay, this is the third problem, right? This is diagonal delta, right? In the previous, when we were talking about the case 2, right? Case 2 is again diagonal. What but that's like more restrictive, right, compared to this case. And this is like delta, 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 right? However, these deltas are, they're same, right? And this is delta 1, delta 2, delta 3, right? And this delta i's in complex, right? So this uncertainty set, or rather the previous uncertainty set, is a subset of this given uncertainty set. Okay, so let's again define our D set. Again, this is the definition of D set, right? And for that specific uncertainty, right, form, we have that type of D set. Okay, and D matrices now we will have they can be parameterized by D1, D2, right? Diagonal real numbers, positive real numbers, right? And here we can see the parameterization. Okay, and this is the Yalmip related information. Okay, here again, let's look at this. For a given gamma, just find me an x. Okay, what was our algorithm? Let's write that to be more redundant. First, determine the structure of uncertainty delta. Okay, and then determine, by using that definition, by using that information, determine the structure of D sets. Okay, and then if we are using Yalmip, right, and determine the structure of, let's call it X, right, X set, and because we know what X is, X is D transpose D, right? Okay, because it's right written here. Oh, that's unfortunate. That's unfortunate. It should have said D transpose D. Let me look at the previous problem. Page 14, right? Okay. Oh, we have that. It's unfortunate. Anyway. Okay, typo. Right? Typo. Okay. I'm going to correct that. Hopefully if I don't forget. All right. So let's try to focus on this, right? And this is our D and this is our D, right? And if we look at the form we have, this is our X. The form of X is in that form, right? So, and this is a real positive number, right? And this is again a given real positive number. So X is parameterized by D1 and D2, and they are positive real numbers. Okay, so we need to just focus on this part, right? We need to just focus on this part. So let's look at the Matlab code. Again, N matrix for a given complex, for a given frequency, get the complex matrix, and again G2 to indicate gamma square, right? Again epsilon. Yeah, that's now different. We have D1 and D2, and they're like scalar one by one, right? And symmetric also indicates they are D1 and D2 are real numbers. But we also, don't forget, need to impose D1 being positive and D2 being positive constraints. We have that constraints to impose, right? Here we just constructed our X, right? And here this line, let's look at this line again, n transpose x n minus g2 x less than or equal to 0, but we write that instead, right? Here we didn't need to impose those constraints, right? We didn't need to make d1 and d2 less than 1000, but I figured, right, just to it came as intuitive to me, right? I thought d1 and d2 they wouldn't be greater than 1000. Of course that's an assumption. I didn't have anything to support that. Yeah, but if I had some error, I would notice that, right? This part would be the first point where I change if I had some error, right? Again, they're like same, right? Comparing the previous cases, and we get the x and gamma 2 or g2, and we get the gamma, and again we assign it to Yalmip SSV and spectral radius and sigma, right? Sigma max. And here this is the, when you type that, Matlab knows that your uncertainty is in this form, okay? And then you use mu SSV and get the upper bound, right? And let's look at the, also since you have like x here, x, right? You can check your x, and what was x? X is like d transpose d, right? Okay, here 0.9057, right? 0.9057, and they agree, right? Okay, so let's focus on the next case. Okay, this is the fourth and mixed case, right? But square case, and this is harder, but compared to the fifth case it's like easier and straightforward. Again, this is our n of s, and for omega equals 1 radian per second, this is our n complex matrix, right? Constant complex matrix. What was the dimension? 5 by 5, right? Okay, so let's focus on that. By the way, you can just find this PDF and docx files, this files, and also Matlab codes in or in there, right? And in this document as well. You can download them from the GitHub link down below, right? Down in the description. Check the description, right? Okay, and 5 by 5, right? So this is 1, 2, 3, and 4, 5. This is 2 by 2, okay? And again, notice that this is square, this subblock square, and this subblock is also square, right? And this is our typical D definition. And since repeated diagonal delta entails or causes like Hermitian, full Hermitian complex 2 by 2 D1 D sub matrix, right? Okay, and then here this is corresponding to that uncertainty subblock, we have D2, and D2 is, due to the reasons we explained earlier, right? Positive real number, right? Again, here this is like one of the easy case, right? And complete like unstructured subblock, right? Unstructured uncertainty. And when you have that, and this is like 2 by 2, right? When you have that, the only thing that commutes with that type of matrix is scalar times identity, right? Because identity computes with every matrix, right? If the dimensions agree, right? And again, this is D3. It's a positive real number, right? And okay, so if we look at the previous problem, that's how we parameterize it. And this is the problem we are focusing on, and this is the information that we need to kind of derive. I mean, this is like, this is it. We don't need to derive anything. But again, let me just correct that. D transpose D, right? This is X, and again, this is X, right? Okay, we are just correcting typo in real time. So what was our algorithm? Just structure of delta, and then structure of D, and then structure of X, right? Okay, so we know the structure of D, and this is it, right? This is Hermitian, right? And this is real, positive real, and this is positive real, right? And here, Hermitian times Hermitian, if you do the calculation, Hermitian times Hermitian is again positive Hermitian, right? And again, this is D2 square, right? And this is like D3 square, and these are again positive real numbers, right? So we basically have, we need to focus on here X. This is the important part that we will use that information when we program. This is our N, and this is a complex matrix corresponding to that given frequency, 1 radian per second. Again, G2 is gamma square. Epsilon is, again, for numerical problems, numerical issues, right? Here we had D1, D2, and D3. If we recall that, D1 was 2 by 2, right? And also Hermitian and complex. Okay. I mean, we don't need to remember, just like it's like over there. It's like, right? Just, and then D2 is this line corresponds to that line, and D3 here, right? 1 by 1 means like scalar, and symmetric is real, but we also need to impose D1, D2, and D3 being positive. Okay, so let me delete those. This is our X, right? Again, D1, D2, and D3 identity, and the dimension of identity is 2 by 2, right? And again, since the dimension is 5, right? 5 by 5 system we had, right? Again, N transpose X N minus G2X. Again, this is it. Okay. Wow, we made a mistake here. Actually, this is interesting. I wonder why Matlab or Yalmip didn't give an error. Anyway, I was going to say, if you realize the mistake, just type a comment down below. But since I know no one is going to do that, I'm going to say that the error is D1, D2, and D3 being positive, right? And we needed to impose that constraints. For example, here in that location. Just give me 1 second, right? And 8, 9, I guess. Okay. Where is that? Yeah. We maybe not like this, but we need to have that type of, right? And also identity for D3, right? For that, we need to have that type of constraints. However, interesting enough, Yalmip solved that I mean, without imposing that constraints, it's like interesting. Of course, don't do that. Don't try this at home. Okay, it's like very dangerous. You would get a wrong solution. Or I mean, you would get a like you would underestimate your uncertainty or underestimate your or wait a sec. You would first you if you write that there are some dangers, and first danger is you would underestimate your uncertainties effect on your system, and this is first danger. And second danger is like you can, and since we are going to use that in mu synthesis, right, you can, there is a chance where you can just overestimate your system's performance, right? Okay, and that's it, I guess. And again, this is like SCP settings and bisection and SCP T3, right? Here, this like the exact same lines, right? And then we check the, yeah, I should have checked that. I bet. Anyway, let's again x, we recover the x and g2 and get the square root of it to get gamma, right? And assign it to Yalmip underscore SSV, and again, and also spectral radius and sigma max, right? Yeah, they're like same. Okay, and you can also check spectral radius and sigma max, right? You would expect that mu variable in sandwich between spectral radius and sigma max. So okay, sigma max is something that you can just, or Matlab can compute, and they're really robust algorithms. However, I heard that this may not be as like numerically accurate as this object, right? So okay, I'm just throwing it out there. Okay, so let's focus on the next problem. Here, this is like the case 5 and mixed case and rectangular. There are some uncertainty, sub-uncertainty blocks. That are like rectangular, not square. Let me sip my coffee. Okay, and this is 7 by 7 system, right? Like close to a real life system. Of course, I mean, you wouldn't have that type of nice transfer functions in real life, I guess. And for here, if you look at this, it's like if you need to really get close to that, just means substitute J1 for S, right? Okay. And 7 by 7, okay? So by the way, I correct that typo that we see in the previous. Is this correct? Wait a second, I'm like extremely confused right now. Yeah, this is correct. 4 and this one, 4, okay. The dimensions agree, okay. And this is square, right? And this is also square. So df and dr, okay? The corresponding d matrices, they are same because these are square subblocks, okay? However, this is rectangular and this is also the rectangular. So, and for rectangular, you also have, I mean, you would generally have full unstructured delta, capital delta, right? Matrix. And whenever you have unstructured delta, you would have some real times identity. However, since this is rectangular, you need to look at the dimensions and 3 goes to that location, and this 2 goes to that location. Okay, so here, for example, this is 2 by 1. Okay, this one goes to that location, and this is like identity whose dimension 1, right? And this 2 goes to that location. Okay, so I mean, since we covered it in the previous video, I'm not going to talk at great lengths, right? And here D1 is positive and Hermitian, right? And then D2, 3, and 4, they are like positive real numbers. And this is DL, D left, and this is DR, left and right? Okay. And this is the parameterization. This is general problem. And now we are going to look at this part. Okay, here is, you can also compare that, right? Just line by line. If you compare that, I mean, we are just doing the exact same derivations, right? And this is the part we need to focus on, right? And actually this is the part. Okay, and let's call it XR, and let's call this term XL left. Okay, and this will be our problem, and this is in LMI form. And in addition to that, for example, this is unknown and this is also unknown, but they are like they appear in linear form. Okay, and there is also some relation between XL and XR. Okay, and so degrees of freedom is like smaller than we think, right? And the worst case, I guess. Okay, so this is the problem here, XR, and they are located in some specific X set again. Okay, and this is bisection feasibility problem. And now we are going to I'm going to state one more time. First, just obtain your uncertainty set, uncertainty structure. And 2, what you need to do, right? Obtain your D structure, D set, right? Corresponding to that. And when we say D, we also mean DR, and DL. Okay. And 3, obtain your X. And again, for general cases, we are actually saying XL and XR. Okay, XL and XR sets, and then solve by using Yalmip. Okay, or any other LMI solver that you prefer. Here, since this is a long expression, it says let us determine the structure of XL and XR. Okay, and this is the DF that we obtained it. We obtained that in the here. This is it, right? On D1 is Hermitian. Okay, so we obtained that. We written the exact same thing. Okay, and then transpose and the same expression. And if you look at this, by the way, there's typo, I'm sorry. All right, so D1, since D1 is positive Hermitian, D1 Hermitian times D1 is also positive Hermitian. Again, nothing changed actually, right? And D2 was positive real number, and D2 square is like again the positive real number. And the same goes for S3, I'm sorry, D3, right? and here there's another typo. It's really annoying. And D4, okay. Here, okay, this is the, all right, and this is XR. Let's focus on XR. We know this, right? This is DF. Oh, another typo. Okay, that's like embarrassing at this point. Okay, so let me look at the dimensions if there's anything wrong with that. I feel like there is something wrong, right? No. Wait. No, it's correct. It's correct. Okay. Let's continue. This is dr. This is dr. Okay. And dr transpose dr. We are trying to obtain the structure of xr. Okay. And this is finally by using the same arguments, right? And we obtain the xr's structure. So this is df and dr. So we know what xl and xr looks like, and we are going to use this. This is like the important part, okay? Right? And these two blocks, right? These two objects that I circled. So again, this is, since this is the final problem, I also express another thing, right? And this is feasibility problem, right? For a given gamma, remember our problem. This is the problem, right? For a given gamma, I'm going to give you some gamma and find xl and xr. If you can find that, that means that gamma or SSV must be less than gamma, right? Less than or equal to, right? Okay, the upper bound of SSV. Okay. Again, we have D1, D2, D3, D4. Only D1 is like 2 by 2 Hermitian and complex. And we also know D1 positive, D2, D3, and D4 also positive, right? Since this is like a matrix, that I didn't want to write directly DI positive. Okay. And we also need to impose that constraints, but I feel like I forget that. Anyway, we are, in addition, usually we would construct our x, right? But here, since this is like mixed and rectangular type of uncertainty problem, right? There are some uncertainty blocks, sub-blocks where they are not square, they're rectangular. They have that type of form, right? And okay, this is, we talk about that, right? XR and XR. We just constructed XR and XR. And then we just written this. Let's look at the structure. N transpose XL N minus gamma square XR 0. Let's keep that in memory, okay? Just keep that in memory. And yeah, look at the structure. It's like the same. Okay. L sandwich between n's, right? And then minus gamma square xr being negative definite. Okay. And since this is like 7 by 7, and this is annoying at this moment because we also need to state D1 positive, D2, D3, and D4 being positive too. However, Matlab and Yalmip together in cooperation, they give me the correct result. And here this is, yeah, wait, not correct. This is a feasibility problem. This is only going to give me XL and XR. because we know what gamma is, we just enter that. This is feasibility problem, right? For a given gamma, I'm going to give you some gamma and determine if that is like feasible. And this is not bisection. This is like way easier. And it's like, it says successful sort. Okay, this is like way easier version of it. And now the real. And to be honest with you, this thing I don't need to. I didn't need to show you. However, since without showing the feasibility, I thought it wouldn't be as complete as I would like it to be, right? And you need to kind of show feasibility and then bisection, right? Bisect over that variable. Okay, so this is like find minimum gamma such that xl and xr, we have talked about their structures, right? And exist. Okay, again, this is our transfer function matrix, and this is our, for a given frequency, give me the complex matrix and the same exact arguments, right? And by using the same exact arguments, and again, d1, d2, d3, d4. Let's get closer. And this is like xl and xr, the same things, right? And here, this is the xl and xr, the exact same formula, right? And again, we not vi, forget to state that d1 being positive, or rather I should say, I should have written d1, since I cannot say greater than, strictly greater than 0, right? Positive, strictly positive, right? Epsilon 1 identity, and identity is like 2 by 2 identity. And again, the same thing, right? d2, d3, and d4. Epsilon 1, epsilon 1, epsilon 1. Okay. Dot. Okay, so I should have written these 1, 2, 3, 4 lines here in that location. So I made a mistake. However, it's working. It's like very interesting. And this is like a bisection problem. And alright, just SCP settings. We are stating that we are using SCP-D3 and bisection. We are bisecting over G2 variables, right? And then we're checking the results. And this is the results, right? We get XL and XR and then G2. And then we get the gamma by getting the square root of G2. And we are assigning it to Yalmip SSV variable. And then spectral radius and sigma max of n. Finally, what was our uncertainty structure? Yeah, this is our uncertain structure. Just 2 by 2 or 2-dimensional repeated scalar, repeated diagonal, and then scalar, and then 2 by 3, and then 2 by 1 full uncertainty. Okay, so here this is like this is 1 by 1, right? This is only 2, and this is in 2 by 3, and that's in 2 by 1. So, and we get the upper bound, and we computed the SSV, structure single value, right, for a given uncertainty type, uncertain set, and for a given complex matrix. Okay, so let me check that if there's anything. Okay, I talk about that in the previous video. And that's it, folks. Thanks for watching, and remember, don't forget to subscribe. And finally, just check the link in the description, GitHub link, right? GitHub link, right? And you can just find this PDF, and also I put it, I guess, in the MS Word form, right? And from that document and PDF, right, you can just get these codes. And maybe I should also put the Matlab codes as well. However, all the information that I explained is in the the documentation, where you can find and download by using